Robertson, Sanders, Seymour, and Thomas came up with a new and more efficient proof using the same basic ideas, but their computer program, I think, runs in quadratic time. So they just improved the computer application of that. So it's kind of interesting that this big result took so long to prove, and they ran into so many problems. Okay, so coloring extensions on planar graphs is based on the idea that if you have a planar graph and some subset of the vertices, okay, that are far apart, so say there's distance at least 100 between them, can we color that set P first and then use the colors assigned to those vertices to also color the rest of the graph? Okay. So that kind of came into play about 13 years ago. And Mike Albertson in '98, so just shortly after this question was posed, showed that it works if the vertices are at least a distance of 4 apart. Okay, so we can color all of the vertices in this set P, and then start moving out from them and color the rest of the vertices in the graph. And we can improve the distance by a small amount. So if we instead want to use at most 6 colors, we can make the vertices a distance 3 apart and still be able to extend the coloring. And then one thing to mention that in general, if a graph can be R colored and vertices of P are, we'll say, far enough apart, depending on what R is, there's some distance that we can determine that for an R coloring of our smaller set P, we can extend it to an R coloring of G. So I mentioned earlier that the research I'm working on has to do with list coloring. So list coloring is a generalization of the idea of vertex coloring, and it was introduced independently by Erdős and Taylor in 1979 and Vissing in 1976. So it's been around for some time. And the main idea is basically for vertex coloring, we're just picking a color 1 through K to assign to each of the vertices. For list coloring, before we do that, we're actually assigning a list of colors to each vertex in our graph. So if we start with a graph and assign some list L of V of however many colors to each vertex, what we want to do to list color it is take a color from the list assigned to that vertex and still have adjacent vertices getting different colors. So really, vertex coloring is a special case of list coloring when all the lists are identical. Okay. So we say if a graph G can be colored from any assignment of list L where the lists are size K, then it would be K-list colorable, or K-choosable is another term used because we're choosing colors from the list. And similarly, we have a list chromatic number, or choice number, noted COS of L or CH of L, related to the least number K, for which a graph is K-choosable or K-list colorable. So one thing we can notice here is that if we know the chromatic number of a graph, the list chromatic number has to be at least that. And that's basically follows from what I just mentioned a few moments ago. If the chromatic number is K, we can just let the list assigned to each vertex of a graph be 1 through K. Then we know that a list coloring based on these lists exists. We don't necessarily know that a list any list of size k will work, but at least these will. So that's kind of a starting ground. But in fact, oftentimes that inequality is strict. So for example, if we consider this graph, which is known as kt2, the complete graph, the complete bipartite graph, with sets of size 2 and 4. So in general, I guess, for a complete bipartite graph, we would take a list of size, in this case 2, or a set of vertices of size 2 in this case, and then of size 4. Connect all the vertices in the top set to all of the ones at the bottom, and vice versa. But none of the ones in the subsequent sets are adjacent to each other. Okay. So let's figure out the list chromatic number of this graph. So if we think about what the chromatic number would be, we can see that 2 colors would be enough, because we could let both of these vertices be the same color, and all of these vertices could be another distinct color. So 2 colors is enough. So let's start there for looking at what the list chromatic number would be. So let's assign these lists to these corresponding vertices and see what happens. Okay, so let's start by coloring the vertex in the upper left. Okay. Say we color it 1. Okay, so that's colored red. Now that means that this vertex on the lower left-hand side, that could either be red or green, has to be green. If we go back up to the top, this vertex that could be either green or purple, now we know that has to be purple. Okay. But then what does that mean for this vertex that's adjacent to the vertex that's already been colored red and the vertex that's already been colored purple, but its list is 1, 4. So that can't be either colored red or 4. So we're stuck. So let's go back to the beginning, that first vertex we looked at.